Hello everyone, welcome to the week 2 of problem solving session. Uh, okay, so today we will mostly focus on asymptotics and secondly there were two algorithms that were done in this during this week. So we will stick to questions related to that. One was the max subarray question. So we will look at some variants of this, and the third was finding local minima. Okay. Okay. So last time we were looking at this uh, sequence called Fibonacci sequence. So just to recall, um, yeah, sequence was f of n is equal to f of n minus 1 plus f of n minus 2. Okay, so and we saw how to efficiently compute the nth Fibonacci number. Okay, so consider for the following variant of the Fibonacci sequence called the Fibonacci sequence, where your nth number is the sum of the previous three numbers instead of two numbers. So this is how we define an. So the question is that you want to design an algorithm to compute this uh, nth number in this sequence. So how would you do that? Any ideas? Okay, yeah. So Goel says we can form the characteristic equation first. Okay, even before that, if you have to do a naive algorithm, the first algorithm would be that you use arrays, and let's say the array an uh, um, is an array of length n, where a0 um, is 0 and a1 is 1. Okay, and then from, so these are the initial values, and then from here what you will do is for I uh, equals 2 to n, what you will do is you will update a of I is equal to a of I minus 1 plus a of I minus 2, and then you will finally output a of I. So that's the first algorithm that you would think of. But here what is the here what is the space that we ended up using, and what is the time that we ended up using? Yeah, sorry. A of 2 is equal to 1, and you will do I equals 3 to, yeah, thanks. So this is the updated algorithm. So what is the space and time for this? Yeah, good. So both of these are order n. Okay, but we want to do better. So from this order n, we want to get sublinear. Okay, so so one suggestion we had was to um, form an equation. So can you think of an equation similar to the one that you saw for Fibonacci? Okay, so recall that in case of Fibonacci, what we did was we wrote f of n and f of n minus 1 as a matrix, and we saw that this was equal to the matrix multiplication of of this matrix A with this vector. So can you think of something similar in the case of Fibonacci? So now I want to write f of n minus 1, f of n minus 2 in similar form. I want to write it as a product of a matrix B and so can you think of what should B be? What is B? Okay, first row is 1 1 1. So this is 1 1 1 because uh, the this row and this column would end up uh, yeah, so this row and this column would end up evaluating to f of n minus 1 plus f of n minus 2 plus f of n minus 3, which is nothing but f of n, which is what we wanted. Okay, and then here you want f of n minus 1, so you just need 1 0 0 because this row will give you f of n minus 1 and you are not even looking at the other two. And yeah, similarly you do 0 1 0 and this particular entry would turn out to be f of n minus 2, which is what you wanted here. Okay, good. So now that you have this matrix, what is your next step? If I want to find the nth Fibonacci number, how will you save time by using B? Yeah, so what you can do is you can keep on repeating this process. So now you can uh, replace this, replace this with the same formula again, and you'll get something like uh, f of n minus 1, f of n minus 2 is equal to b square times f of n minus 2, f of n minus 3, f of n minus 4, and you can keep on repeating this until you are left with okay, I don't know what, I'm assuming this is n minus 1. Okay, you can back calculate this, and this will be f of 2, f of 1, f of 0. Okay, so your job is to find this, and one idea that Raghav is suggesting is that we will do matrix multiplications. So you compute b square, then you compute b cube, and so on. But those are n multiplications, right? Like order n multiplications. So do we know any tricks to make it faster? So we want to compute b to the n minus 1. Okay, what do you mean by transitive closure? Do you mean repeated squaring, Goel?
So, that would mean that when I move from the element 1 to other elements by using one element in between, that would be the value of b square. And the meaning of b cube would be that, traversing
Yeah.
from an element to the
So
other
yeah,
element.
as Minal points out, so in the previous case, what did we do? Instead of multiplying this n minus 1 times, which takes order n steps, what we did was we did repeated squaring. So what we did was we first compute b square, then you compute b to the 4, then you compute b to the 8, b to the 16, and so on. Okay, and you jump to the nearest power of 2. Okay, so uh, is that clear? So how many steps are these? If you are doubling at every point, then what is the number of steps? Correct, log n. So from order and steps, we have made significant amount of progress. We don't need order and matrix multiplications. Now you only need order, log, and many uh, multiplications to be performed. And notice that if this n minus 1 is a power of 2, then here is your answer. Okay, you'll end up with the answer. But what if n minus 1 is not a power of 2? That can also happen, right? So what is the trick that we used earlier? Yeah, so the point is, if n minus 1 is a power of 2, then we are done. Okay, but if not, then what will you do? Because if you take one more step, then you are jumping much ahead, right? This is, and your um, actual value is somewhere here. Okay, actual value is somewhere here in between 2 to the k and 2 to the k plus 1. mm, b to the n minus 2 times b. But what if b to the n minus 2 is also not a power of 2? Because what if n minus 1 is, let's say, 50? So if, let's say, n minus 1 is 50, then the previous power of 2 is 32 and the next power of 2 is 64. So we are somewhere in the middle. Okay, so I'll give you a hint. So look at how to write any decimal number as sum of powers of 2's and see if that helps you. Yeah, yeah. So yeah, as one of you pointed out, Meenal. So what you will do is express the number as sum of powers of 2, which you can always do. So in this case, how do you write 50 as sums of powers of 2? So 50 is 32 plus 16 plus plus 2, correct? So that means if you want to find a to the 50, if you want to compute this, it is same as computing a to the 32, multiply it with a to the 16, multiply it with a square. So these values you already know because they will appear here, right? So these values are already known to you, and then you need to perform, in this case you are performing 3 additional multiplications. So for a number as large as 50, you are only performing 3 additional multiplications. So in general, you can express these as sums of at most log and um, many matrices, um, and so you are additionally performing order, log, and multiplications. So initially you performed order, log, and multiplications in order to compute the values of all of these, right? And now you're performing additional log and multiplications because your number need not be a power of 2, so you may have to perform a couple of uh, order, log, and multiplications at most. So overall your algorithm still runs in order, log, and time. So is this Is this okay? This is basically whatever you did for Fibonacci, but the point is that it works even here, right? The same idea uh, works.
So I have three
Yeah.
questions here.
So yeah, Goel has asked one question with, what about the complexity of matrix multiplication? So in case of Fibonacci, you only had um, a 2 cross 2 matrix, right? So no matter what stage you are in, your matrix is always a 2 cross 2 matrix to be multiplied with the 2 cross 2 matrix. So this is uh, order one operation. In this case also, your matrix is 3 cross 3, and you're performing a multiplication with a 3 cross 3 matrix. So this is again constant time.
So to what
So yeah,
extent?
that factor will be multiplied, but since it's order 1, we will avoid that. Good.
So to what extent can I mean, extend this sequence? Like say here fn is equal to fn minus one plus fn minus two plus fn minus three. So to what extent can I extend this? Say in general, if we talk, say then fn is equal to fn minus one plus fn minus two, so till fn minus k kind of a thing. So then would be able to solve I mean such a recurrence relation using the same strategy.
Yeah, good. So, okay, so in general, if so, extending the idea, consider the relation an is equal to an minus 1 plus, let's say, an minus k. So now your matrix is going to be a k cross k matrix. Yeah, and here you have a into an minus k. Here you'll have n minus 1. Okay, so are you okay? So again, this is the matrix B that we have, or let me call it A. Um, so you're going to perform multiplications of k cross, multiplying 2k cross k matrices. So as long as k is small for you, if it's a constant, then you are still in order 1, but otherwise it could be um, k to the 2.5 or something, right? 2.8, I think. Okay. Yes, so yeah, I forgot to mention at the beginning. Yeah, these sessions are recorded and will be uploaded on YouTube. The link is, you can find it in Swayam portal. Okay. Any other questions regarding this discussion? Okay, so there's a question that says, if there will be an online exam for this. As far as I know, the way the NPTEL exams work is that, towards the end there will be one exam where you need to go to a center that's allotted to you. But if there is someone who has more clarity on this, please respond in the chat. Um, Otherwise, you can ask this on the Q&A portal, because I'm not completely sure, but to the best of my knowledge, I think there will be an offline exam. Okay.
Ma'am,
Yes.
ma'am, you have told that in if we are not able to express the n minus one is equals to two power k, like we should express it as the sum of powers, no, ma'am.
Yeah,
If
yeah.
it is being the biggest number, how can we express?
Uh,
Like we can't add or multiply so many powers like that.
what do you mean by biggest number exactly? Like n is like how large?
Means like 50 is between 32 and 64. Like that any other number above 50, which is
Okay,
not the square of 2.
okay. So let's say n minus let's say n minus 1 is between uh, is let's say 20 uh, is let's say 2000, which is also not too big, but just for the sake of demonstration. So in between, like, what are the powers of 2 in between between which it is embedded? So this should be between 2 to the 10 and 2 to the 11, I think. So correct.
Yes, ma'am.
So now we are not even looking at like I mean, with respect to 2000, this 10 and 11 are very small numbers, right? It's logarithmically small. So how many products, like how many matrices did we compute here? You will do b square. Okay, from b you will go to b square, b to the 4, and so on, all the powers of 2 until let's say you are here at b to the 11, right? So how many products did we do? Roughly 11.
Yes, ma'am.
And similarly here you're going to write this 2000 as a uh, sum of some subset of these, right? Not all of them will appear. So for example,
Yes, ma'am.
so those are at most 11, right? At most 11 many. Some of them like don't even appear here, no? So
Yes, ma'am.
right, so again these will be at most log n multiplications again. So that's why you are like exponentially doing better.
Okay, ma'am.
Okay, okay, good. um okay, so okay, so we will move on to some questions on asymptotics, because that was a major focus on the week 2 content. So you're given 4 functions, and um, order them in ascending order of like the increasing order of complexity or growth. Okay, so between a and b, which is smaller? Yeah, so Goel says a is log n to the 1 by 2, and b is log n to the 100. So clearly um, log n to the 1 by 2 is smaller. Now between, yeah, good. So okay, so between b and c, which is smaller? Okay, so a bunch of mixed answers. So one way to check whether uh, which is smaller is that you take logarithm on both the sides. Okay, so if let's say log of some quantity x is less than log of some quantity y, that means x is less than y. Okay, so therefore one way to compare these two functions is that you check whether among the logarithms of these two, which is smaller. So what is log of the first quantity? This is 100 times log n. What about the logarithm of the second quantity? So this is n minus log n. Right, so now the comparison is between these two, in between 100 log n and n minus log n, which is the smaller one? Oh, sorry, thanks for pointing out. Yeah, sorry, this is log n minus log n. Yeah, thanks. uh, hmm. Okay, so now you have that yeah, so now you have that between b and c, uh, this is smaller. But note that the reverse of this is not true. If x is less than y, it need not be the case that log x is less than log of y, because when you go to a logarithmic scale, uh, some quantities that were larger may sort of get flattened out, so you'll lose the sense of difference. But anyway, we'll not get into it right now. So note that this is only in one direction. So if log of one quantity is lesser than log of the other, then you can say this. Okay, and now in between c and d, which is smaller? Good. So between C and D, D is smaller. So D should definitely be before C, but D could be here or it could be here. So what is the correct place? So for that you need to compare B and C. Okay. So let's compare log n to the 100 versus um, n to the mm, okay. Okay. So yeah. So as you have seen in class, I think if f of n by g of n, limit n tends to infinity, um, is equal to 0, that means fn is um, order g of n, right? That means your quantity in the numerator is much smaller than the quantity in the denominator if you look at its behavior when n tends to infinity. That's why this quantity is close to 0. Okay. Yeah, you're right, so this should be little low. Yeah. So uh, yeah, so let us look at what happens here if you have log n to the 100 divided by n to the 1 by um, yeah, 1000. So what is this quantity?
ఒకసారి మళ్ళీ మ్యామ్ మ్యామ్.
Okay, so yeah, I think okay. So yeah, as some of you have pointed out in the comments, you can use your L'Hopital rule and so on, or whatever. I mean, uh, and find out that okay, and check that this goes to 0. So so your quantity here would uh, come out to be n to the 0.001. So that's the order. But yeah, okay, I don't have the rules fresh in my mind. That's why I'm not doing this. But check out. Um, okay, so there's a question: what is the behavior of hyperlog compared to the small powers of n? Mm, by hyperlog, you mean like powers of log or log n or something? So you want to compare n to the k versus log n. Yeah. So here, your I mean, previous trick of taking the logarithms would work, right? I mean, if you take log on both the sides, you get versus k log n, and this is clearly a much smaller quantity. But is that the question that you were asking, or what do you mean by behavior? Is
I don't know, but then I heard that the hyperlogs behave differently than a simple log function. Like, say, if you go first with the log, if you take log n raised to the power 5, so
hmm.
it could be entirely different than the log of n, the behavior of the log. But I don't know because I don't know whether it's true or not. But then the hyperlogs start behaving like polynomials after a call. I don't know whether it's true or not. Like,
In
say,
terms
if you
of
take
growth, in terms of growth, is that what you're saying?
in terms of the growth of the function.
Um, that is counterintuitive, no? Because, like, if there are, I mean, the more the logs there are, like, the slower and slower the function becomes. Whereas the polynomials are faster growing compared to that, right? So,
So maybe say, what if we compare the log n raised to the power k with n raised to the power
log n to the power
k?
k
Yeah.
versus,
Log n whole. Log n is a single quantity. Yeah. And versus n
I
raised to
see.
the power. Clearly n raised to the power k would grow faster. But then, what would be the behavior of the log n raised to the power k?
Okay. In that sense, you're saying you're thinking of this as a polynomial. If you think of this um, as your capital N or something, then it's behaving polynomially in terms of log n. That's what your point is.
Yes. All right. Yeah. I understood the things. Yeah.
Okay. Um, okay. Are there any other questions? So, is this fine with everyone? Okay. Good. So, okay. Hmm. So for each of these four sub questions, um, you have to find the relation between f of n and g of n. That is f of n order g of n, or little o of g of n, or omega of g of n, or little omega of g of n. You can write your answers in the chat or unmute and let me know. I'll just write the definition side by side. Yeah, so okay, I'll wait for others as well to write. Okay, actually I should be writing it this way. Okay, so there are a couple of answers. Okay, so as some of you have pointed out, f of n is equal to n to the log of which is nothing but c to the log n. Okay, and this is nothing but g of n. So indeed they are the same functions, but in terms of, okay, and there's also theta, right? So in terms of these five quantities, you have to choose one which is correct. I mean, which is yeah, tight. uh, so okay, so for the part A, which is the, yeah, what about others? What do others think? Okay, good. So um, okay, so you say that f of n is theta of g of n if f of n is order g of n and g of n is order f of n. So okay, so therefore f of n. Okay, so what about b? Okay. Hmm. Okay, what about others? I see some answers which say theta, some answers that say little o. Okay, both are saying little o. Okay, so between f of n and g of n, which is a intuitively which is a larger function? Um, okay, so okay, so we are comparing 2 to the n square versus um, n to the 22 to the 2n. Okay, so this is our f and this is our g. So uh, yeah, so I mean if you take log and so on, you will notice that this turns out to be n square times log n, and this turns out to be 22 to the 2n times log n. So this is an exponential term, whereas this is just a quadratic term, right? So this is a much larger function. Okay, so you can bound f of n by c times g of n. Another way to look at this is you look at the limit of f of n by g of n, and you'll find that this will turn out to be 0. You have 2 to the n square here, and you have n to the uh, 22 to the 2n, right? Okay, so this factor, this term here is a much larger. This um, I mean, it has exponential term in its exponent, so this is a much large uh, yeah, this is log 2, sorry. Yeah, then you're comparing n square versus an exponential term, so this is still much larger. So you have f of n is little o of g of n. Does that make sense? Why this is not order the big O, but rather little o? Okay, good. So um, what about C? Okay, so versus n square. Okay, okay. So if you take, let's say, log on both sides, this is um, this is at most log n to the log n, and if you take log of this quantity, this will turn out to be log n times log n, versus this will turn out to be 2 times log n, and in between these two, uh, this is a larger quantity, right? So so uh, so you have f of n.
This
um,
log calculation is not clear. How did you write
oh,
this
sorry,
log?
sorry, what is the question?
So this calculation of the log n factorial is not clear. So this is the factorial of the log n as a whole.
Hmm.
So how to write that?
So, if I roughly approximate uh, log n minus 1, log n minus 2, and so on, all the terms by at most log n, then you have product of log n many terms, each of uh, each of value at most log n. Mm. Or
Then,
if you use the Stirling's approximation also, you will end up getting this. Mm.
then how did you write this quantity as log n, log of log n, and
Yeah, I was trying to compare this quantity with this quantity. Um, I was comparing these two on the logarithmic scale. But yeah, so I was looking at the log of these two quantity. If this were larger, then we would have concluded that f of n is little o of g of n. But that's not the case, right? I mean, this quantity is turning out to be larger.
how?
Mm, as in the log n thing is there on both the sides. So the comparison is between log n and 2. So clearly log n is a faster growing function. Um,
Because of
right. But this will not work for us because um, I upper bounded this quantity, right? So I'm looking at a quantity which might be larger than this and then comparing this large quantity with this. So it is possible that maybe okay this is larger, but that does not imply that this is larger. So we will have to look for some other ideas. So this was just an attempt. Okay, this does not work. mm, so then what you will need to probably do is find limit n tends to infinity. um, by n square. Okay, and okay, so let me okay, I'm just trying out on the fly, but if you have ideas or answers, you can feel free to share. I'm just trying to arrive at the solution. Okay, this will work. Okay, so yeah, Rajesh has pointed out as well, what you'll do is use the Stirling's approximation like we did, but don't use the upper bound. Use the lower bound. So you know that this quantity log n factorial is sorry. So by using this approximation, we know that by using this part, you know that log n factorial is going to be at least 2 to the c prime times log n. So how did we arrive at this? We are just replacing n here with log n. So blindly look at n wherever it is and replace it with the log n, because the function that we are originally looking at is log n factorial, right? So this is what you get from the Stirling's approximation. And now compare this with your original g of n, which is n square. So which is larger? So we'll do the same thing that we did earlier. You take log on both sides. You get um, here you will get log n log n times some constants, and here you get 2 log n. So clearly this is a much larger function, because log n with log n is comparable, but this is a much uh, larger term. So you have that fn is at least equal to this quantity, which is strictly greater than uh, the log of your, or let's say log of f of n is strictly greater than c times
G of n.
sorry, yeah, what did someone say? Had a question? Okay, so that means f of n is uh, omega g of, is little omega g of n. Yeah. Is this fine with everyone, or do you want me to explain any part of this? Okay.
Ma'am, as this is greater than or equal to, isn't it, ma'am? So it is the big omega, I think.
Yeah, so this part is greater than or equal to, but this part is strictly greater than, right? So that means log of fn will be strictly greater than log of g of n.
Okay, okay. Thank you, ma'am.
Okay, so let's do the final part as well. So on one hand, you have n to the log n by log n, and g of n is n to the 1 by 10. So the base is n for both of them, so you are really comparing the exponents. So log n by log n versus 1 by 10. So this should be straight. Uh, okay, so there is one answer which says f of n is little o of g of n. Any other? Okay, so when you say omega, do you mean the big omega or little omega? Okay. Okay. Good. So let's look at the comparison. So for part D, you have n to the log n by log n versus versus n to the 1 by 2. So we can say that we will compare log n by log n versus 1 by 2. Okay, so which is smaller among the two? So here on sorry, uh, yeah, so here on numerator you have a smaller quantity, and on denominator you have a larger quantity. So for example, if n were 2 to the 16, then this quantity is going to be 4 by 16, which is 1 by 4, and this is still 1 by 2. Okay, and if I mean if n is increasing, then this quantity in the denominator is increasing at a much larger pace than that of log n. So this can get as small as as n tends to infinity, this will tend to 0, right? So uh, if you look at limit n tends to infinity, log n by log n by 1 by 2. So this is your f of n and this is your g of n. This is going to be 0. So that means f of n, by definition, f of n is little o of g of n. Yeah, so this log of log n is actually is it's not log n times log n, right? It is actually log of log n, which is a much smaller quantity. For example, if n is 2 to the 16, let's say, then this will be log of 2 to the 16, which will be log of 16, which is 4. Whereas if you were to use this, then your answer will be 16 times 16, which is 256. So this is a faster growing function, and what we are looking at is log n. So that's why they won't cancel off. Hope that answers. Okay, so is this okay with everyone? Does everyone agree that um, okay. So before we move on to the next question, any discussion point related to this question itself? Okay, so okay, so assume that you are given two functions f and g, where f of n is order g of n. Okay, suppose this is what you have. Then from this, what can you conclude about okay,
I think previous to this one, wherein you showed the relationship between Fn and Gn, and you wrote Fn is equal to big O order of Gn or the small O order of Gn. Previous to this one, I guess.
sorry, I
Previous,
couldn't hear you.
previous to this one.
Okay.
Uh, so I mean to say that when we write, say Fn is little O order of the Gn, then instead of there exists a C, there has to be for all. I mean, for all C's. So when we define little o and little omega, so there is different condition than the big O and the big omega, and instead of there exists a C, there is for all C's, I guess.
Right, but if you look, these are reverse of each other, right? If f is order g, then g is omega f. So here, if you want to show that fn is little omega of g of n, you can equivalently show that g of n is little o of f of n, which is what happened here. There is some constant c um, for which no after, like, when n is large enough, after a certain point n0, this quantity will always supersede this quantity.
So that is the point I want to make here, that while showing the relationship for the little omega, For the big omega, it's fine. That we just need to find one value of the C, and for which this inequality holds true. However, to show that something is little omega order of the GN, this inequality must hold true for all the C's, whichever C I can think of. So then this inequality holds true. Is okay. Is this right? Or I mean, because in the previous slide you wrote there exists a C for the little notations as well. So I need to say that instead of little C,
Here, here, right?
yes, okay,
Yeah.
here, yeah.
So here also, if you look at it, I mean, look at it in the reverse way. If you are looking at 2 log n versus uh, log n log n, um, that so how will we show this? There is a C such that um, for all n greater than equal to n0, 2 log n is at most, sorry, is strictly less than uh, hmm, C times.
Yes, so that is what my point is. Instead of there exists a C, it should be for all C's. For all C's, in case of the little o and the little omega solutions, I mean, merely the existence of just one C is not sufficient to show that this Fn is little omega order of the GN. This inequality must hold true for all possible values of C. So instead of there exists a C, I think this should have been for all C's, and which is inequality.
Mm, I'm not sure about it now because um, I can read the same thing. I can read the same thing. I mean, with this quantifier, but with the inequality reversed, right? And
So this uh, reverse thing will work. Reverse thing is like, but
so,
then, yeah. So my only point here is that I don't have any other apprehension except that this, in case of the little o and the little omega, instead of this there exists, this should be for all C's. And for the big O and the big omega, that's absolutely fine. And we just need to find one C, and for which this inequality holds true.
mm, okay, I mean, before writing this in the reverse order, that is what I had in mind. But now I'm thinking, why should it be that? I mean, why are we only reversing C? Then the quantifier should also be reversed for n, but that does not make sense. So,
We can
uh,
discuss it afterwards or yeah.
I
So this,
couldn't.
this is just an observation. You can move to the next question. Yeah.
Yeah, yeah. So I'll address this maybe towards the end. I'll look into the definition also. But as of now, I feel like, I mean, this makes more sense to me because, I mean, with the same quantifier, um, and looking at the inequalities in the reverse way, you are getting the definition. So, but yeah, let me come back to this later. Okay, good. Um, hmm. Okay. So you have two functions, f of n and g of n, where f of n is order g of n. So what can you say about the log of these two quantities? Okay. Okay. So when you say less than g of n, do you mean less than equal to or strictly less than? Okay, so let's look at the answer. So let's put this into definition. So that means there exists a c greater than 0 such that for all n greater than equal to n0, log of, sorry, f of n is at most c times g of n. This is by definition, right? So now what you do is you take log on both the sides. So this gives you that log of fn is at most log c plus log of g of n. That means if I choose c appropriately, choose c prime appropriately, we'll have that for all n greater than equal to n0, log of f of n is at most c prime times log of g of n. That means log fn is order g of n. So yeah, as both of you observed correctly. So is this fine with everyone? So this, the first property is true, that if f is order g, then log of f is also order g. Okay, so what about the second question? Okay, so one answer says no, that this is false. Any other answers? Okay, so if you think this is false, can you come up with a counter example? Show that it is not order uh, 2 to the g of n, it is some other quantity, omega or something else.
So if we take Gn is equal to say c multiplied by f, and then 2 raised to the power c multiplied by fn would become what? Say uh, c and multiplied by 2 raised to the power gn, and 2 raised to the power c would be a constant. So since it would be a constant and less than or equals to inequality would still hold true. And so this is true. This is true. My only point here is that when we take 2 raised to the power something, so then that 2 raised to the power gn will become what? 2 raised to the power c multiplied by 2 raised to the power fn. And so that will become, because then every function is bounded by itself. Okay. So in that sense, this is big O order is true, as well as big theta is also true. I will only need to say. Function is bounded by itself from the upper side as well as from the lower side.
Yeah, so yeah, but to give a counter example, it only suffices to show that let's say fn is
I think it is a theta function, ma'am.
Okay. Okay. So let's take this example. Let's say that f of n is equal to n by 2. Okay. Then what is 2 to the fn? This is 2 to the n by 2. Mm, and let us look at gn, which is let's say n. Okay. Then what does 2 to the g of n become? This is, sorry, yeah, this is 2 to the n. Now if you compare 2 to the n by 2 and 2 to the n, you'll get that 2 to the fn is um, little omega, sorry, yeah, is little o of 2 to the g of n, because this is because limit n tends to infinity, uh, f of n by g of n is equal to 2 to the n by 2 by 2 to the n, which is equal to 0. So by definition, sorry, this is what I meant. But if I were to think of f of n as 2n and think of g of n as n only, then what you will get is f of n is little omega of g of n. By the same idea, if you look at the limits, you will again get a 0, because 2 to the n by 2 to the 2n will become 0 eventually. So you get this as well, and then you get, sorry, 2 to the f of n is little omega of 2 to the g of n. So none of the, I mean, so because it's little o as well and little omega as well, so we can't say that it is theta. If it were order as well as big omega, then it would have been a theta. But at the moment, all we know is that this is not true, because there is one example which demonstrates that this is not the case. So is this fine? Yeah, I think Anjali and Goel had similar reasoning. So is this fine with everyone?
Ma'am, if we take fn is equal to n and gn also is equal to n, then what is that condition we're going to get? Equal, isn't it, ma'am?
Yeah, then you get equal. But uh, but the question is this true unconditionally? That is, no matter what f of n you take, no matter what g of n you take, is this always true?
No, that is, of course, it is wrong.
Huh.
But this can be a theta, isn't it, ma'am? Theta function.
Not for all f, but yes, if you choose f and g to be both n, then yes, it will be a theta function.
Okay, ma'am.
Good. Yeah. Okay. Any other questions? Okay. So what about the third part?
I think it is big omega, ma'am.
Okay. Okay. So if you take f of n to be n, and let's say g of n is also n, then you are comparing n square versus c times n. So this is larger, so you'll have that f of n square is omega of g of n. But is this always true no matter what f or g you take? Can I take some other example and find that this is not like little omega? Yeah, so yeah, I think even square root will not work, because when you take square of square root n, you'll have n here, and then you have square root n here. Okay, yeah, that will also work. Yeah. No, sorry. So if you compare, if you take f to be square root n, uh, and g to be also square root n, then f of n square will be n, but this is square root n. So they are not the same according to the order notation. This will be omega of. We will still be in the same case, but as Goel has pointed out, if we take a constant function, so if f of n is 5 and g of n is 10, then even if you square or whatever power you take, you will still be some order 1. So order both f of n square as well as g of n, both of them will be order 1. So then you can't say omega, then it will be order n for that choice of functions. But anyway, this claim is not true, so this is false. So this example demonstrates that. Okay, is this fine with everyone? Okay, so yeah, I think this question will address the question that you had, Goel. I think your point was that there exists n greater than equal to n0. Sorry. Such that f of n is at most c times g of n. Then I can write this in the following way, that is at least 1 over c times f of n, and this is equal to c prime times f of n. So there is a c prime greater than 0 such that for all n greater than equal to n0, g of n is at least c prime times f of n. So for this reason, I think this should be the definition of omega of f of n. Like the quantifier should remain the same as far as
In case of the big notations, this is fine.
hmm,
But in case of the small notation, it is there in the definition itself. And this has to be for all C's. This is a part of the definition. Nothing but little to do with equality.
I can't hear you clearly.
This is the part of the definition for the little notations. For the big notations, it is fine. That Fn is bounded by the Gn from the upper side, the Gn is bounded by the Fn from the lower side, and both the bounds will be asymptotically tight.
Okay.
So in case of the big notations, this is fine. But in case of the small notations, little notations, there this is there in the definition itself,
Hmm.
that for all C's greater than J, and then for all C's greater than J. So this is the part of the definition while defining the little variations, little o and the little o.
Oh, I see. So you're talking about, so your question is not even about this being little o and this being omega, right? You're just talking about little o in general.
Yeah, in case of the little o, so when we define that f is little o order of the Gn, then and if we use the same definition, it's okay that instead of less than or equals to, we'll write strictly less than. But along with the strictly less than, the
Hmm.
another condition would be that for all c is greater than g, we will say instead of there exists is.
Yeah,
That,
yeah, that uh, that is correct. Yeah.
that is my point. That only the strict thing is just one aspect, that Fn is strictly less than the Gn. The other thing is that this inequality must hold true for all values of not just the values of this.
Yeah. Okay. So, okay, so I will leave this as an exercise. Um, and this one also. Okay, maybe this maybe we can take as a final question on asymptotics, and we can move on to um, the algorithms part. So, so do you think uh, there exists an epsilon such that the following is true? Okay, so what is the reasoning uh, for no?
So we compute the limit, limit n tends to infinity, and then log n by n power psi. Let us take the derivatives of both the steps. That becomes finally the value came out to be 1 upon n raised to the power epsilon.
Hmm.
And in order to show that this log n is big in order of this thing, so 1 upon n raised to the power epsilon should be equal to infinity. So now we are looking for a value of epsilon. For that limit n tends to infinite, and then upon n raised to the power epsilon.
Yeah, can you mute unless you're trying to speak? Okay, sorry. So, yeah, so as both of you, Meenal has also answered in the chat. If you take logarithm on both the sides, here you have log n, and here you will have c times epsilon times log n, and oh, So this is a larger, this is a larger function, right? I mean, if you choose your C prime appropriately, this is the one on the right hand side is your larger function. So uh, yeah, so this cannot be true. So you'll have that log n is little o of n to the epsilon, no matter what epsilon you choose, for all epsilon greater than 0. Um, yeah, so this is false. Okay. Okay, so I hope this is fine. So recall your maximum subarray, some subarray question, which was as follows. You were given an input, uh, an array A of n integers, uh, and you have to find a B subset of A, or um, S such that um, summation of um, AI is from this is maximum over all choices of I and J. So basically, given the subset, you are going to find a smaller array. Sorry, this is not subset. I want, sorry, subarray. Yeah. So given an array A, you want to find a subarray, a contiguous subarray which is sitting inside A, such that if you sum up the entries of all the elements here, you will end up with the largest value. So the way we did this was to write. We maintained an extra array. Um, so the idea for solving this was that uh, we maintain S of I, which is the maximum sum of a subarray that ends at I. So for example, if this is your array A and these are the entries, -2, 5, 6, -10, and so on. Let me not write all of them. So what does S look like? What is the maximum sum that you can get for a subarray that ends at this position? It is -2. What about a subarray that ends at this position? What is the maximum sum you can get? Yeah, 5. So you have two options, either take -2, 5, in which case the sum is 3, or you take 5. So the maximum is this. What about, let me just fill the 4 entries. So what is the value at S of 2? $11. And what about S of 3? so okay, so notice that you have to end your subarray at 3, so you have to include 3. You cannot exclude the element at 3. Yeah, so in this case the sum is 1. So then what you will do is at the end, so you will fill the entire subarray, the entire array S in this way, and then in the end find max of S of I, where I is from 0 to n minus 1. Okay, this is what you will do, and that will give you your answer.
Hello, ma'am.
Yes.
Ma'am, I have a doubt. When we are taking for index 1, we took maximum from 3 to 5. But in index 3, we are taking 1. But it should be 11 now.
In index 1, as in here, that was the first thing you
No,
mentioned.
ma'am. S array index 1, we took maximum element, na 3 or 5.
Yeah, so what are all possible arrays that will end up, uh, um, which will take 5? It is either you take both of them or you only take 5, correct? So
Yes,
this
ma'am.
so this was maximum, right? So among these two, so what about S of 3? What are all possible arrays that end at 3? You can take minus 2, 5, 6, minus 10, or you can take 5, 6, minus 10, 6, minus 10, and minus 10. These are the all possible options that we had, right? Among these, this gave us the maximum value. This was 1. This is
Oh,
minus,
okay,
yeah,
ma'am.
this is minus 4. This will be uh, minus 1 as well. Yeah, so this was our maximum.
Ma'am, just a confusion. We are not doing the cadence algorithm, right?
Yeah, that is what that is exactly what we are doing. So i just
Uh,
need to I just need to write how we are calculating S of I.
okay.
So one line will make it the same algorithm. So what is that? You'll How do you update this, right? So S of I is nothing but max of S of I minus 1 plus A of I, or it is A of I. This was the step uh, in the algorithm that you saw, right? So this is why you were able to update uh, entries in order one time.
Okay, ma'am.
Okay, so so that was the idea, and now the question is, instead of finding the maximum sum, let's say I want to find maximum product in a subarray. Okay, so instead of instead of sum I want product. So instead of the sum here, I want to find product of AKs from I to J, which is maximized. So what are the changes that you will do in the algorithm?
Will multiply.
Okay, so one one suggestion is, instead of addition we will multiply, which seems to be the most natural thing to do. But let us check out on this input itself. So let me erase this, and sorry.
We can have maximum negative number also.
Hmm. Okay, so let me just uh, demonstrate with an example why this fails, and then we will implement what you are saying. Okay, So this was our array, and um, instead of um, doing any major changes, if we just do the following, if s of I is implemented in the following way, it is maximum of s of I minus 1 times a of I comma a of I. If this is what we do, then this entry is minus 2. What about the first entry? Entry at index 1. uh, yeah, this will be 5. What about the next step? Will be 30. And what about at this point? Okay, so we are applying this formula for now. So what is s of I minus 1? S of I minus 1 is 30 and a of I is minus 10. So this is minus 300 versus minus 10. Okay, so you will end up writing minus 10 here. Sorry, minus 300 here. No, sorry, max is minus 10. Yeah. Okay, so you will end up writing minus 10 according to this algorithm. But what is the correct answer? So this is supposed to capture maximum product of subarray ending at I. But if you, yeah, like some of you answered in the chat, if you multiply all four of them, what is the product you get? You end up getting 600. Okay, so this is clearly, so the correct answer should have been 600, but if we apply this formula, then you end up getting something else, right? So this is faulty. So how do we correct this? um, yeah, I think Meenal had an idea. Do you want to share?
Yes, ma'am, we can keep negative numbers also, uh, apart from positive numbers.
Yeah, so the idea is that you will keep two arrays now. One will keep, so this does not work because negative numbers behave differently for products, right? So now the idea is that maintain two arrays. So let's say s1 is my first array and s2 is my second array. So s1 of I denotes, this is the same thing, this is so let me just call it s only, and let me call the new array as p. So s of I still denotes the same thing. So um, okay, so it denotes the maximum product of a subarray that ends at I, maximum positive product, of course. And by p of I, we want to capture the minimum negative product of subarray ending at I. So if we do this, I hope the intuition is clear to everyone. if the current integer I have is positive, then the maximum value will be, if a of I is positive, then maximum value will be s of I minus 1 uh, times a of I, because this was positive and this is positive, so net positive term will be this. And if a of I is negative, okay, if a of I is negative, then I want to keep the minimum negative term. Okay, so in this case, for example, that minimum term should have been minus 300. So this is what I want to store, so that when I encounter sorry, not minus 300, what is this, 30 times 2, this is minus 60. So I should have stored this minus 60, which is the minimum minimum negative product, so that when I see that minus 60 and minus 10, I'm going to multiply the two of them and get the correct answer, which was 600. So if a of I is negative, then how do I find the maximum positive? I'll take the minimum negative sum that I can find so far, multiply it with a of I. Both of these are negative, so in the end you will end up getting the max positive term. So is this idea clear? uh, so the only change is this extra array, and our condition changes depending on whether ai is positive or not. Okay, so if you want to write this in terms of um, okay, in terms of recurrence, then what you can do is mm, okay, so okay, so when I want to keep some sort of sign, I want this sign to be minus 1 to the mm, sign of a of I. So let us see what this is. Okay, if a of I is a positive sign, uh, okay, mm, okay, so a of I okay, so both of these cases, a of I is something that we are anyway going to multiply with, so this is what I'm writing on the um, I mean outside the bracket. Now next thing we want to make sure, if I want to write this as a single relation, is that um, I want to select s of I minus 1 between s of I minus 1 and p of I minus 1. But okay, anyway, the recurrence actually does not make sense as a, you should be able to do this by playing something with the signs, but my point is um, anyway the recurrence does not make sense, because when we write in as a form of an algorithm, you will end up writing something like this, right? So you will end up writing um, so your final algorithm is that for all I from 0 to n minus 1, what you are going to do is update as follows. S of I is going to be maximum. Okay, yeah, there will be a check. Okay, so S of, okay, doesn't matter. So S of I is going to be the maximum of S of I minus 1 times AI and S of I minus 1, and P of I is going to be the minimum of uh, P of I minus 1 times AI P of I minus 1. And then once you are done with this in order and time, because each of these steps only looks at the previous values and then does a simple multiplication, and max and min operations can also be uh, performed similarly. So in the end, what you're going to do is go through each entry in S of I and in S and P and find the maximum one. So we're going to find max over both the arrays. Yeah, sure. You can definitely optimize this algorithm in terms of space as well. You don't need to uh, store this as an array. You just keep a max counter, and every time you see a new product um, which is larger than your previous product, then you are going to update it. So you can get rid of both the arrays and do this in order one space. uh, yeah, that is correct. So is the entire algorithm like clear now? So this is also an order n step, and so overall time is order n, and currently space is order n because I'm using two arrays, but yes, this can be improved to order 1. So is this algorithm fine? Okay, so I will remove this so that there is no confusion, but yeah. Okay, so the only difference was that we use this extra, the idea of keeping the minimum negative product as well, and in the algorithm where you were only updating the S of I earlier, you are also updating P of I now. Okay, so the zeros and all will be taken care of in the loop itself, right? I mean, the max function will take care of um, which is larger in the end. Okay, so okay, so this is one variant where um, I mean, you just needed a small modification, um, and the way to do that is try the obvious thing like we tried earlier. We tried to only use one array and then we failed, and then we realized, okay, what was an issue? The issue was the negative numbers behaving absurdly. So then we tried to come up with this new idea. So um, so here is another variant uh, of the maximum subarray problem, where instead of um, allowing your subarray to be of any size, earlier we did not have any restrictions. So let's say, okay, I'll remove this for now. Let's say you want at least k elements to be there. So where does the previous algorithm fail? Can you think of an example or something why we cannot use the original algorithm as it is? So for example, my k is 4. Can you think of a counter example?
It was giving answers of subarray containing two elements also, so it was failing.
Yeah, correct. So for example, I could have 1 2 okay, actually -1 -2 and then 4 and 8. Let's say this is my subarray, then so this is my array, and the original algorithm, okay, maybe I'll just add few more entries. So the original algorithm will say that the maximum sum is corresponding to 4 8, which is only two elements, but here I'm insisting that the subarray size must be at least 4. So in that case, the correct answer should have been -1 -2 4 8, the sum of which is 9. So this should be the correct answer according to our algorithm. So do you see how we can modify the um, okay, let's not even talk about modification. What is the brute force algorithm?
Take all subarray of size k or greater than k and take their sum
Hmm.
and take max.
Yeah. So how many subarrays, or how much time would that take?
O of n squared.
Mm, is that n square or n cube? Because um, okay, anyway, the number of subarrays is at most n square. So yeah, that's correct. So you would yeah, end up using something like order n square. If you store the sum and reuse the sum and so on, then yes, you can do it in order n square. But um, I want to do in order n. Then how do we take this leap? Um, okay, so one obvious thing is that um, let's say your array is index term, so up to k minus 1 there is no, I mean um, again, let me say that S of I denotes the maximum sum of a subarray, but with the constraint that it contains at least k elements. So maximum sum of a subarray ending at I and containing at least k elements. Okay, so this is how I want to denote s of I, and as earlier what we will do is we will take max of s of I at the end. That will be our final answer. Okay, so all these values are invalid because there cannot be a subset of size at least k which ends at k minus not k minus 1 but k minus 2 at least. Yeah, so only at k minus 1 you have seen at least k elements. So the maximum sum here will be summation of I is from 0 to k minus uh, k minus 1. Okay, and at this point you will have choices. Now you have several options to work with. Your maximum subarray sum can be 1 to k, or it can be 0 to k, or it, yeah. And as you keep moving ahead, you will have more and more what you can think of as sliding windows, right? Um, so if you are looking at an index j, then the maximum subarray sum can be it will have to be the max of s of um, s of I, where I is from um, yeah, you have to go at least mm, you have to go at least k steps before this, right? mm, okay, no, this is just k, yeah, sorry. This is, sorry about the confusion. Okay, so so any ideas about how do we go about doing this? Maybe this does not even make sense, so I'll just remove that. It's the same thing. Okay.
We'll have maximum sum till I minus k, and then we'll separate it and take maximum.
mm, what is I here? So you want to find maximum sum of I, so you'll find uh, I minus k. Is that what you're saying?
Yeah, something like that.
mm,
Max of I minus k till the time it's getting 0.
mm, huh. But if you do that, then we are not doing better than n square, because for every index j, I'm going to have to look uh, I mean look backward.
For that we can use, no, fine.
uh,
It's n square.
hmm. Yeah, because what could happen is that currently this was your maximum sum, but maybe if I exclude this element and look at this, then maybe I'm getting a better answer. But uh, I mean, I will have to do some updates, like remove some elements from the sum and so on, to find out what is the correct maximum at this point. So so what you can do is think of okay, so what is it that I want to find out? We want to find um, sum of the subarray, which is sum of ak k is from I to j, and this is what we want to maximize. We want to maximize this sum. Okay, so this can be written as summation of ak, where k is from 0 to j, minus summation of ak, where um, k is from 0 to I minus 1. So essentially from this 0 to j sum, we are removing the previous sum, and that gives us the um, sum of that subarray. So uh, if I were to think of this quantity, okay, I mean given an array, let me write this sum, the consecutive sum of all the elements up to that point. So this is simply adding one more element at a time. So for a fixed j, this value is fixed. This is basically the sum of all the elements up to index j. Now this is the quantity that is varying, and additionally we want to make sure that this I minus j is at least k, right? Because you want to find only such sums. So this is an additional condition that we have, because we are looking at k side subsets. So this is the quantity that we are finding out, and that we want to find out, and this is assume that this is a fixed quantity. So um, so what is it really that we are uh, removing? So from this so let's say I'm finding out the maximum subarray sum up to point j. I can think of removing this part and so on, but I cannot go all the way up to here and remove all of it, because I want my subarray to be of size at least k. So what is the correct position to cut off? I'll cut it off at j minus k. Okay, so this quantity here which we are removing can be a quantity this small, or it can be 2, or up to j minus k. It is some part of it that we are going to remove, and look at the quantity which gives us the maximum sum. So is this fine? The why we are writing it as this?
Yeah.
Okay, so that means this is a fixed quantity, and because I want to maximize this sum, that means we want to minimize this quantity, right? So that means your task really is to find out what is the correct value between 0 to j minus k, whose sum is as small as possible. So this is similar to what you did earlier, right? You were finding, in some sense you were keeping track of minimum product as well. So here you want to keep track of minimum sum until that point, and this is something you can do in order n. Okay, and uh, yeah, and once you have that, you will update this. So instead of think of it as this problem, instead of finding maximum sum of a subarray, this quantity is finding minimum sum of subarray, because we are going to subtract it in the end. So this is the general idea, but I'll stop here. Try to try to make this more concrete, and finish the algorithm. Maybe we can discuss this next time. Okay, and also try out the other one, where you want to find maximum subarray sum, where there can be at most k elements in the set, and the point of both these variants that we saw is that um, it's generally the same idea that requires a little bit of change to work for different requirements as such. So so try both of these. uh, Maybe we can discuss this next time along with the other questions. Okay, so next we will meet on Tuesday itself, same time, 7 p.m. to 9 p.m. Yeah. Okay, so yeah, thank you all.
Thank you, ma'am. Thank you very much.
Thank you. Um, okay. Okay, then I will end the call. See you next time. Okay, this recording will be uploaded on YouTube along with the notes. Okay, bye all.